Alright, welcome back. Now we're going to do the second discussion problem. So I'm going to call this problem quick search because it's basically randomized quicksort, but for binary search. So it's very similar to the nuts and bolts algorithm from Jeff's notes if you want further examples, and it's very similar to the analysis of randomized quicksort that you can find in many of the books. So if you want further examples of the analysis, feel free to check those out. So let's show that quick search does O of log n comparisons and expectation. So to remind you what quick search does is it will pick a random element between 1 and n. So let's call this element k, and k is between 1 and n. It then will compare k to x, and then if k is equal to x, where x is the thing we're searching for, then we're done, and we return it. Otherwise, if k is less than x, we want to check the left part of the array, so we recurse on 1 through k minus 1. So specifically, this is a of k, because we're going to look at indices. And then otherwise, a of k is greater than x, in which case we recurse on k plus 1 through n. So it's exactly like binary search, except instead of the middle element, n over 2, we're going to look at a randomly chosen. We'll call it a pivot. So if you're familiar with quicksort, this is very similar idea of a pivot as there. Okay, so this is how the algorithm works. We want to analyze it. Traditionally, when you're looking at randomized algorithms, you want to use indicator random variables. So these are very convenient. So let's just say xi is equal to 1 if and only if we compare I to x at some point in the algorithm. So quick search. Now, if we know this happens, then in total, the amount of comparisons we could do would be 3. So we compare the ith elements to x, then we might have to compare it to do the less than and greater than. We could also think of this as just one big comparison. It doesn't matter. So in big O notation, this will be equivalent to what we want. So in particular, if we let t be the total number of comparisons, then we have that t is exactly the sum of all of these xi's. So we're going to break down the problem of figuring out the total number of comparisons by just looking at whether a specific item was compared to x or not. And of course, if this is not true, then xi will be equal to 0. So when I say an if and only if, the alternative is xi is equal to 0. So we will call these Bernoulli random variables, but doesn't really matter. It's just a special kind. So the nice thing is linearity of expectation tells us that this will exactly be the sum of the expectations. And because they're Bernoulli, this will just break down to the probability that xi is equal to 1. So this is a nice benefit of using indicator random variables to break our problem down into pieces. Because no matter what, we can use linearity of expectation to make it into a simpler problem. So now we really just have to figure out what is the probability that xi equals 1. So first thing we need to do is let's choose an element j such that aj is between x and is between aj plus 1. So remember, when we're doing binary search, the element doesn't actually have to be in our list. it could just not be there. So we're doing this just so in the case where x isn't in the list, we roughly know where it should have been for the analysis. Of course, if x is in the list, then we could take either side to be x, whichever one is equal to its value, doesn't matter. So we're going to choose j so that this is true. And we won't really worry about the edge cases, so it could be that x is smaller than everything, in which case there is no aj. In that case, we could define a0 to be minus infinity or something, but it really won't matter. So we'll just go off this assumption. So in particular, let's define dk to be the point in the algorithm when we know xi. So in particular, if the kth stage of the algorithm, we end up directly picking I as the pivot, so if I is the pivot, at stage k, so stage could be a recursive call or a for loop depending on how you model this, but so let's say k is a recursive call. So at stage k, we've chosen I as the pivot, and so we know for sure that xi will be 1 because we directly compare it to k, or compare it to x. On the other hand, if we know for sure it's determined at stage k, but it wasn't the pivot, then it must be the case that it was going to be ruled out. So either it was the pivot or we ruled it out. So it was either on the left of, so we could have had that the actual pivot, let's say it was L, we had AL was less than X, but AI, or not even I, but I was greater than L, or we could have had that AL was greater than X, but I was less than L. So essentially it was on the wrong side. The other case was it was on the correct side, but if that was the case, then we would have determined it at a later stage. So if I was on the correct side of x, then it contradicts dk is when xi determined. So in a sense, if this happens, we could recursively continue our proof to find the correct position when it was determined. So we know for sure it was either one of these things. So if I is the pivot at stage k, then of course there was some probability it was the pivot, and there's a probability it wasn't the pivot. And this is how our case analysis is going to go. So in particular, we can break it down even further. So if I is at most j, then it'll be the pivot exactly when we chose I out of I through j. So in total, there are a total of j minus I plus 1 possible indices we could have picked out of this range, and we chose exactly I. So that happens with probability j minus I plus 1. Alright, I just wanted to make a quick clarification on why we have to choose I out of the range I through j from case 1 where I is at most j. So remember, we're assuming that we determined xi at this stage k, so that's what dk implies. So if xi is determined, we couldn't have anything to the right of j or to the left of I. So if we picked an index that was, say, I minus 1, and so our range was I minus 1 to j, Well, it could be the case that the pivot was I minus 1, in which case we'd recurse on this section. And so i's truth, whether xi is 0 or 1, is determined later, which again contradicts the fact that dk, this is the point where it's determined. Similarly, if we had j plus 1, we could have chosen j plus 1 as the pivot, which doesn't necessarily rule out the possibility that I will be compared. So because we're choosing dk to be essentially the minimal time, or the last time that we're looking at I, we know the range of indices must be this. And because we're specifically looking at xi being 1, we know that I had to be chosen out of these. So just wanted to add in that quick clarification. So in the second case, we have that j is less than I. And so in particular, we need that one of j plus 1 through I. We know one of these is chosen, and the one we need to be chosen is I. So out of all of these total elements, we want I to be chosen. So in total, since they're picked uniformly at random, for it to be one of these, it'll be exactly I minus j plus 1, which will just be 1 over I minus j. And you'll notice that neither of these probabilities actually depend on k, and so we can actually just conclude that the probability that xi is equal to 1 will be exactly 1 over j minus I plus 1, or 1 over I minus j. And this happens exactly when I is at most j, and this will happen exactly when I is greater than j. Alright, so now we want to plug this definition into our expectation for t. So if we do that, again recall that the expectation is equal to the sum of the probabilities, and so we'll get exactly the sum of all I from 1 to j of 1 over j minus I plus 1, plus the sum of all I from j plus 1 to n of 1 over I minus j. Now if you break down these two sums, it'll turn out that this one is exactly hj, and this one is hn minus j. So you can see that by plugging in values. So if you plug in I equals 1 here, you'll get 1 over j, and then you'll get 1 over j minus 1 will be the next term, and it'll keep going till you get to 1 over 1. So this is exactly hj. And similarly, this one will start at 1 over 1 and keep going until we get to 1 over n minus j, which again is this. Now both of these numbers are smaller than n, so we can upper bound this exactly by 2 h of n. And we know that h of n is O of log of n. So that gives us in total that quick search will do an expectation O of log n comparisons. And the critical idea here was breaking the problem using indicator random variables. And then we can use linearity of expectation and the fact that Bernoulli random variables have simple expectations. And then just bounding the probabilities of each event happening gives us exactly the analysis we need.